Hello and welcome to the graph related videos of VitoshAcademy. Today we'll be talking about beam search and this will be our last video for graphs. So what do we have here? We have the generate graph plot that we are using. We have the raw data that we are using. And we have the highlight path in the data once we have something. So to say, in our story, we are always trying to start from A to P, and depending on the algorithm that we are using, we either find the best way or the worst way, or one of the ways. Anyway, so far we have discussed and showed depth first search, breadth first search, Dijkstra and A star, and today we'll be talking about beam search, which would be our fifth algorithm for finding a path in graph. So what is the problem? Why is A star not the best one we're working? A star is actually pretty good, no lie. It finds the perfect path, so what can be better than perfect? Well, there is a catch. If you remember, A star actually checks and remembers everything. So in a massive video game or a chess engine with billions of possibilities, A star would eat up all your RAM and crash the computer before finding the solution. And what is better than A star? Well, what is better is beam search. I mean, imagine that A star is a rich explorer who can hire infinite scouts like this one, for example, starting hiring a scout for B, hiring a scout for C, hiring a scout for D. Well, beam search is a budget explorer. It says I can only afford to track, let's say, 2 paths at a time. So at every step, it looks at all the options, picks up the top K, which in our case is, let's say, the beam width, or in our case 2. So it picks up the top 2 and it fires everyone else. It uses a fraction of the memory this way, but it runs at a risk. It might accidentally fire the scout who was on the right path. Well, yeah, this is true. So enough talking and let's start programming the beam search. So first, let's read our data. It is the raw data here. We should somehow read it. Yeah, this looks okay, but not the best one. Just noticing here. Okay, so how do we read it? Okay, we need to get the lines and we need to say, okay, strip based on the new line and split it also based on the new line. And let's see, what do we got? Lines. Yeah, we get it correctly. Let's continue. What else do we need? Number of edges and the information about them. So lines 0. Okay, that's correct. Dot split, and it should be 1. 1 should be enough. So number of edges like this is 21, and it should be an integer. With Python it is so easy. Yes. So now let's take the edge lines, and the edge lines are gonna be from lines from 1 to 1 plus number of edges. Great. These are the edge lines. So starting from AB1, finishing in YZ5. Let's see. Starting from AB1, finishing at YZ5. The next one are the heuristics, and the last one are A and B, which are the start and the end. So to say, that's pretty decent. What's the third one? Node lines. Pretty pretty much same like this, but starting from here and finishing here. Do you see the mistake I'm doing? Yes, I hope you see it. A and P are not needed. A50 is the first one. Let's just check. Yeah, great. So what do? We need -1. Yeah, and now this one is not there. And now the start and the end are fancy. So start and end, we just take the last one and we split it. And if we use end, we'll see P, because P is the end one and A here is the start one. Okay, so far so good. Let's do something else here. Let's get the heuristics. The heuristics would be a dictionary, and let's loop full line in node lines. Pass. Just remember what was in the node lines. Okay, great. This is what we get. So we need to make some kind of a dictionary where this is the key and this is the value. How do we do this? Well, we would need to split it. So line.split. Yes, and we will be having two. So the key and the value. We can say, for example, key value, line key, line value, like this. And then heuristics. Then here we would have line key equals easily line value. That's the fancy part in programming. You can always try and see what's going on. Okay, the value should be an integer. I'm just curious if I have done it like this. Would it work? It would be so ugly that I wouldn't want it to work. Okay, let's continue. Now it's time to build the graph. So full line in edge lines. Let's see what do we got there. Okay. Yeah, the graph should be also a dictionary, and it would be having something like this: part A, part B, and then this would be part cost. So we have start, part end, and part cost. And this one we will be saying line.split. So if part start is not in graph, then graph part start equals to an empty dictionary. That's great. And in general, graph part start append. What do we append? Well, we append part end and the integer part cost. This piece of code is, so to say, used. Just one more append. Also in the previous 3 videos, at least. Okay, and everything looks great. For example, A, we see that from A we have a road to B, to C, and to D. and from D we have 2 rows, and yeah, our graph is rather simple. From A we have 3, and from D we have 2. Rather simple, but it should be working. So let's write the algorithm here. So we have start F. We will be using heuristics. If you want to see the heuristics video, just go to the previous A-star algorithm. It would be interesting. I somehow assumed that you would actually take a look there and watch all the videos one by one. Yeah, so start F is 0 plus heuristics from the start, and it should be around 50. Why 50? Because it says so. Yeah. This thing get start and 0, it actually return, if here we don't have a value, it should return the 0, which is actually a good option if we have problems with the heuristics somewhere, but we don't have them. But still, let's keep it this way. Okay, current beam, which is the value, which is pretty much the nodes that we are currently considering, and we are currently considering 2 nodes. Okay, these 2, actually 1 node, the A node and its value. Yeah, so this is the current beam, as simple as it is. Okay, we have cost so far, and it should be from the 0. We don't have any costs. Let's see how it looks like. Looks good, I would say. And we should have where it came from. Well, start came from nowhere, because it's the first one. It looks fancy as this. And just counting the steps. Because we can. Counting the steps is good. Okay, now the fancy loop. While current beam step equals step plus 1, or if you want to be fancy, plus equal 1. Okay, printing some information would actually make sense here. Step, and then the step. I mean, I like this. And beam width. And then current beam. I'm just thinking. Beam width I haven't given. I'll give it right now. The rest should be okay. Let's see. Yes. No. Oh, actually I have current. I have beam width here. Yeah, this is what you shouldn't be doing in programming. For example, just interrupt. Is it interrupted? Let's see. Yes. Oh no, we have managed to interrupt it. Okay. I'm just thinking, where is the beam width? Actually, it's not here. Actually, beam width equals to interrupt. Okay. I'll just put a break here, so it breaks. Or just restart. Let's see. Okay. One of the problems when we are live, in a way, raw data is not defined. You think so? Really think I have defined it, but yeah. Okay, just a quick redefinition of everything. Thanks for the idea for having a break here, because it saves a lot of nerves and time somehow. Okay, so let's continue. What do we have? We have a list of next candidates, and the list in Python is like this. Okay, so first we need to expand everyone in the current beam. So for the current beam, how it was looking like this. Okay, so far it's just one, but we need to expand everyone and just take a look what can we do. So parent f, parent node in current beam. So parent f is this one, parent node is this one. Yeah. Okay. If parent node equals end, just reminding you what is end if you're following with me, end was p because it was the end. Then if we found a goal in our beam, we are done. So that's great. In a strict beam search, we might want to finish the layer to ensure optimality, but usually here we simply stop at the first hit. So let's print something like go found. We're happy. That's fair enough. And after printing, we need to reconstruct the path. And it's a fancy reconstruction. I know this one. And of course, path.reverse is what actually helps us to get the path in the correct order. And here we return path and cost so far. Returning 2 is okay. I somehow understand that we are not on a function, which is for the time being, I guess, okay. So I'll simply decode this one and say here print. Yeah, fair enough. Now let's continue. If we are not on the end, actually we need something to do. And this something to do is to keep the current beam pretty much active. Not active, but changing. We should be putting stuff there, so to say. Yeah. So for neighbor, that's a tough word. I always comment on it, but in graph set parent node, this one, and empty list, and we have new G. So if you want to get more information about this new G thing, you should probably take a look at the A-star video. I have explained them there. Because so far, parent node plus weight. If you are bothered to take a look there, this new G is the value to which we have the real value, so to say, without heuristics. For example, in order to get here, our value is, so to say, the real one, whatever is written on the A to C plus whatever is written on the C to G. A to C is 5 and C to G is 2, so the value should be 3 for G. Yes. Yeah, so the weight is this one. Okay, in graph, just reminding you what do we have in the graph. We have it like this. So A to C 5, so cost so far, plus weight C to G, for example, yeah. C to G 2, yeah, 7. This should be our new G. Yeah, so far so good. We need a standard check, pretty much checking whether this path is better to the neighbor. With other words, is this a better path to this neighbor? And how do we check it? With a simple if. Cost so far, get dot no, cost so far dot get neighbor, and here I usually put some kind of number like this, but we can be fancy and we can put that. You see, Python actually knows infinity. I don't know how it does it, but it's obviously some kind of a floating object, as everything in Python. Okay, so cost so far neighbor, 2 taps, do the magic, it shows up. This is the new G. And came from is the information where it came from, neighbor, parent node. Like this. Yeah, new f equals new G, new f is new forecast plus heuristics. This is pretty much the whole formula in A star. Real plus heuristics. G plus H equals F, if you have to say it officially. I have explained what the dot get does. I mean, if it is a none, it would give a 0. In case we don't have the heuristics, in this case we have it. So next candidate. Come on. I don't see the next candidates. Control and space. Next. Okay, next candidates. I just pressed tab, but obviously it takes some time here. Okay, so far so good. Now we go into the cut. And the cut is the thing between the beam search. If you remember at the beginning, I was explaining something that in this case we only have 2, so to say, people that we can hire to check. So this means that we have to make some kind of a cut. So this cut is going to be done here. If not, next candidates, then simply break, and we are free from the loop. Next candidates dot sort. The key is the lambda. This is a way to sort something, and we sort things like this. Let me show you what this means. Where were the defined next candidates? I'm just thinking, okay, they are just empty here. I'm just thinking how to show this thing. Graph dot sort, and then key lambda where x sort on. Okay, it's already sorted alphabetically. What can I sort by so I can show that something is lambda len of x, which fall lambda x len of x. Yeah, let's give it a try. No, dictionary doesn't have an up. Yeah, exactly. That's how it is. Dictionary doesn't have an object sort. So if I have to show something like something like this, so quickly showing something. Then A looks like that, completely unsorted, but if we want to sort it, then it should be P equals A dot sort key equals lambda, and we sort by 1. Let's see what is B. Okay. Yeah, you see it is completely sorted now. -2 is the smallest one. This is the next one. This is the next one. Okay, so that's the idea of this one here. So next candidate like this, and then we have current beam equals next candidates, and then beam width. Okay, I remove the break, and here it should be, I'll make it now a function none, and the cost so far great, so it means that here I'll make it also. And how do we make everything here like a function? That's a good question. Would be called function in Python solve beam search. Data is a good name. Beam width like this. Okay, everything else shift it a bit and put a bit like that. Okay. Ta-da, ta-da, ta-da. The graph in front of the graph, when we define it, heuristics in front of the heuristic. This all type of style, like all the variables on the top, it's really VBA, and hopefully nothing else. Full parent, everything, current beam, everything looks okay. Most probably I have done a mistake somewhere, but I'm not sure. The way to check it is just 1. I would say let's take a look. Shift and enter, and now the time to see, so to say, what's going to be happening. Just let's say path or path original equals solve beam search. We need path original and cost so far. Cost so far is just cost. And we're going to say, I remember it was raw data, what we were passing. And the beam width is an optional parameter. I'm going to stay with 2. Dictionary object has no attributes set. That's interesting. I can swear the code was working before, but that's the favorite thing. New G cost so far parent node plus weight. This is, no, the problem is here. For neighbor weight in graph set parent node. It's not set, it is get. I'm just thinking about stuff. Yeah. different than programming, obviously. And let's see path original and just cost. Okay, so we're turning none and we returned cost so far. Yeah. What can we do to make it better? We can remove the none. I don't know what I was thinking about, but it's better this way. Looks better, everything is better. And we see our path is A0, B1, C, and then D. A, B, C, D. And it worked. A, B, C, and then D. That's interesting. Okay, path and cost so far. Okay, we always get the path, but we don't get the cost. Okay, now I got it. Why do we have like this? Yeah. So if we don't have the thing for the path, we just return the none. Okay, fair enough actually. Let's take a look. Okay, and somehow it looks like we have a problem because we didn't find anything. Why is this like this? If you understand what happened, it just looked in the cost so far in everything and it says I'm up to here. And the real reason is, I would say, not sure if we are putting something in the current beam. So while current beam, yes, we are not putting something, I'm not sure. Should be this one, next candidates. Yeah. Let's see, print current beam. Now I got it, most probably. Yeah. The problem should be, we should not be in the loop. We should be somehow outside the loop. But in this one. Okay. Okay. Path original and what else? Path original and cost so far. Actually, no, it's okay. Step 1 with current beam. This is what we got. Then 6B and 25C. And the path is A, B, C, D. Let's take a look. A, B, C, and D. Okay, now we are again on the old place. Okay, I'll just, should I research on these places? I'm just thinking, are you really following the way you should be following, or is it better if I just do it this way? I was thinking, okay, this is probably how it should be. Yeah, path original. Yeah. Okay, somehow we are lucky. We just did this. Sometimes Python is problematic, but not today. Functions like this are too big, and debugging is a bit tougher, especially this way. But okay, let's summarize and see what we got. Step 1, this was our current beam. Step 2, this was our current beam. And at the end, we were really happy that we have found the goal, and the original path that we have is ACGHP, and it worked. ACGHP. Highlight path in data. Yeah, okay. Just showing you what this function is, and then first the original data, raw data, and then the path. I'll just call path result. So path result in underscore, and then getting the generate graph plot full. You see A, C, G, H, and P. Everything's good. Everyone's happy. We have managed to get this one here. You can write a comment if you understand why it was not working before and why it works now. Print current beam. Print current beam is actually useful. I'm not going to touch it. Yes, I have, so to say, something interesting. I have prepared something called the greedy trap, which is completely different visualization from this one. We need to create a graph where the greedy search with a width of 1 fails, but beam search with width of 2 succeeds. I'm just thinking how to do it. I'll just copy the thing here, and I'll call it risky data. Tada! And just to understand how it looks like, let's take a look. Generate graph plot, and simply say risky data. Yeah, graph visualization start to go. Okay, I get 2 just because of some mistake probably in the coding. Doesn't matter. I'll just take a look at the 1. You see, from here, then if we go to the next one, we go up to here. And if we have beam search with just 1 beam, it should actually find this one here. But if we have beam search with 2, it should go to the cheaper way, which is in total 3. Yeah, looks good to me. Yeah, this is the good thing for having a structure in the graphs, pretty much always saying at the beginning how many nodes do we have, and then naming our things. Okay, start is a good name for a start, go is a good name for a go, and then we have also the heuristics. This heuristics here is actually perfect because it's also from the to go is also 100. Okay, now let's take a look and see what will happen if we say path 1 and underscore, because we don't need the cost so far. And this one will be, so beam search, come on, with the risky data and beam width of 1 or just 1. Shift and enter, this is what helps. And then we'll have path 2, pretty much the same. but we'll be using the tool. And I'll just run it once more so it's visible what is what. Yes. Yeah, obviously step 1, step 2, step 3, step 4, step 5. We see that it actually finds the goal, but with an interesting scenario. Yeah, so to say, let's see, path 1 is A, B, E, F, P. But I don't have A, B, E, F, P. I have these guys here. Yeah. Why is it like this? Data beam with solve beam search. I should be having risky data twice, I guess. Yeah. What about path 2? Now I know. Yep. If you have something in the comments, just write it. With me here is that I'm taking something called data, but I'm here using raw data. So in the beam search function, I'm always referring to this one, which is a mistake. I should be referring to the argument in the function. If you know why this happened, then write something fancy in the comments. And this is also what I was hoping to get. So path 1 and path 2. You see, the paths are different. Path 1 goes B, C, D, and then go. B, C, D, and then go. And path 2 actually is actually the risky one with start A and go. Start A, go. Why is that the case? Well, that's the interesting part. With 1, the algorithm starts at start. Then it sees A with heuristics 100 and B with heuristics 1. It sorts them. B is actually better, so it deletes A. It moves down to the B path, so to say. It eventually hits the goal, but via this route. And with B it is different. It keeps both A and B because of the budget allowing 2 scouts. In the next step, A reveals that the go is right next door. The scout path actually still continues here because it is in the node. You see current beam, and then everyone is actually happy. Yeah, who would have expected this one actually, which is kind of strange. I mean, I would have expected that more scouts would bring us better results. Well, not in this case. Probably we should change something here. Let's see before the summary. And actually the truth is a bit different, of course. It's never like this, never what we expect. Just returning everything in path 2 and path 1 and see the difference. Path 1 actually goes through B, C, and D, B, C, and D. And yeah, the go is at 103 this way. If you go B, C, and D, because we have go of 100, just because this one actually looks scary, but it is not. Yeah, let's see path 2, what happens? Yes, it is with 2 and it's great. Yes, this one with the heuristics, it's a fake one. Start to A is actually just one. Yes. And the D to the go is 100. Yeah, it's an interesting one, but the thing is that the more beams you have, the better the data, which was actually as expected. Great, now let's make a summary of the last graph video in VitoshAcademy for the graph season, so to say. First, we had the generate graph plot, which is a function that we used in all the videos, graph raw data, which we have here, and it's plotted. Probably I should use this one. Sorry for the interrupting the review, just thinking. Fig. Yeah, like this. And we only put it once. Great. Then we have the highlight path in data, which we are using sometimes. Then the beam search, which is with a default beam of 2. We read our things. It's important to always use the correct names in the parameters, because if you do what we did in the videos like 20 minutes ago, you would be failing. Then we read everything. We define heuristics and graphs correctly. We define the start, the current beam, the cost, and where it came from. It is important because current beam is actually later appended to, like here, with the next candidates cut by the beam width. Now we enter the main loop, which is where the magic happens. And yeah, this step counter is not that important actually, not even returning it. I'll just remove it for the noise, to cut off the noise a bit. Okay. Actually, it was important because in the printing we are doing it. Yeah, I'll return it. Yeah, better. Then we print some information on what exactly is happening where, and then we do our important magic with the beam first, with the beam search. It's not DFS, it's not BFS, it's just beam search. And at the end, we simply return. Here we return none if we haven't found the path, because we don't have anything to return. And then cost so far, yeah, the important cost so far, which in our case is this is the path, and this is the cost that we found. Yeah, the optimal values. What did we try later? We tried something called risky data manipulation here. What is actually important about this risky data is to know that the heuristics is actually lying to you. It's not what it seems like, but from D to go we have 100 here, and A is actually perfect. So what we were hoping to get is if it sees that A is 100, that it would go this way, and seeing the go, it should strike the go. And this is exactly what happened with beam search, with one beam. Yes, it found our data on the expensive way, BCD, and then go. And for the go, it was costing 103. But for path 2, with 2 beams, we found a magic, because we have 2 explorers. It actually found the quick way with the go of 2, because this one A was wrong with heuristics. It was actually just 1 from A to go, talking about this one here. Yes, so far so good. Thank you for watching. Enjoy the rest of your day and take care of yourself. Goodbye.